Thank you for the introduction and thank you for the invitation to present. I'm really glad to be part of this workshop and looking forward to the next 2 days. So yes, it's a bit late for me, so hopefully, I won't blank out during my presentation, but please bear with me. Yes, so my presentation today will be about modeling effects of light on the circadian system, and I will particularly focus on the incorporating effects of light spectrum. And you have seen different versions of this slide today already, and I suppose by the end of the day you will see many more, but just for the sake of brief introduction, you know that circadian clocks are extremely important in our physiology because they pretty much control the timing of all the biological processes. And the main environmental cue for our circadian clock, which is located in the brain, is the light-dark cycle. And as we know, the endogenous periods of our circadian clocks are on average in population slightly longer than 24 hours. And it's the solar 24-hour cycle that entrains us to the, this precise periodicity of 24 hours every day. And the main circadian clock in the brain, or the master circadian clock, it also synchronizes the peripheral clocks in the organs and other cells. So it's very important to keep the synchrony of all these different oscillators. But as you know, circadian misalignment does happen when we have misalignment between the environmental cues and the endogenous circadian rhythm. So this, for example, can be seen in shift work or jet lag with, like lifestyle choices when you choose to go to sleep too late, for example, and wake up early, or you can have circadian disorders that result in circadian disruption. And the results of those are actually quite bad for health, including increased risk of cancer, diabetes, cardiovascular disease, and mental disorders. So it's best to avoid circadian disruption as much as possible and minimize it where it cannot be avoided. And for purpose of understanding circadian misalignment and circadian rhythms and effects of the light-dark cycle or the circadian rhythms, it's useful to use modeling, or at least I think it is useful. I'm a physicist, so I do modeling of sleep and circadian rhythms. And so modeling can be used to understand the misalignment and as well as dynamics of the circadian clocks and make predictions, for example, for shift work and jet lag. And one of the, probably so far the best model existing for the circadian oscillator was developed now almost 3 decades ago by Kronauer and his team at Harvard. And this model is based on so-called van der Pol oscillator, and it accounts for the effects of light on the circadian phase. And it mainly incorporates the effects of timing and the intensity of light. So for those who are not familiar with the model, it takes the photopic illuminance as an input, or like for most people, it's known just as illuminance. This light input affects the photoreceptors in the eye, which convert between ready and diffuse state, and they send input to the oscillators or the circadian variables in the SCN, which then together produce the circadian output. And this model is great for prediction of circadian phase, for example, at shift work and jet lag, but what it does not account for is for the spectrum of light. And we do know that light spectrum or wavelength composition does matter when we're talking about circadian rhythms. So as you have seen already in 2 previous talks, the circadian system or the effects of light on the circadian system are mediated by these iPRGC cells that contain melanopsin. And the key point here is that the sensitivity to light of these melanopsin containing cells is different from the rods and cones or from the visual system that we have in the retina. And this you can see here. So this is the comparison of the 2 sensitivity curves, one for the visual system and the other one for the non-visual or melanopsin mediated system. So why it matters is because for different light sources, then the photopic illuminance and melanopic effects will be different. Just to show you a quick example of this, here we can see the spectral power density profile for like a usual fluorescent lamp. And if we look at the photopic sensitivity, so here with shown with the green, it peaks around 555 nanometers. And then if we look at the melanopic sensitivity curve, it peaks in the blue range. So the circadian system is more sensitive to blue light. And then, of course, depending on the spectral power density profile, it can be a sort of larger or smaller differences between the photopic illuminance and melanopic illuminance, which is why I think in models we need to account for the melanopic effects of light rather than use the photopic illuminance. And thankfully, we can calculate melanopic irradiance or illuminance if we know the spectral power density and the sensitivity of melanopic cells. So that's pretty much just integration of the spectral power density weighted by the sensitivity curve. And so what we have set out to do is to take the original dynamic circadian oscillator model and incorporate the effects of light spectrum rather than just the photopic illuminance. So we have replaced the photopic illuminance input with the melanopic irradiance, which can either be provided directly if you have the values or calculated from the spectral power density of a light source and the melanopic sensitivity profile. And that actually was very sort of easy switch for this model. And that was because the original model was calibrated against experiments, which almost all of them were done using the same light source, namely the fluorescent Philips 4100 lamp, which means that we were just able to adjust the constants in the model to convert from the photopic illuminance to melanopic irradiance. And after doing that, we wanted to test whether our new model with melanopic irradiance would be able to reproduce experimental results for other light sources as well. So to do this, we mainly look at the phase response curves and dose response curves, which you probably know are the sort of key types of experiments to study circadian response to light. So in terms of the phase response curve, so these are the results for the fluorescent light, 6.7 hours of exposure, where light is applied at different times of day, and then the phase shift is assessed after compared to before the light exposure. And on all the plots that I show, you will see the markers show experimental data from published studies, and then model predictions are showed with either the solid or the dashed lines. And here you can see the old or the original photopic model. It does like very good predictions for the fluorescent light, and our new melanopic model using melanopic irradiance as an input, it produces identical results for this fluorescent light, which is what it should do because we just recalibrated pretty much the model for the same light source. But then our hope is that the melanopic model will perform better when we consider other light sources. And an example here is using the monochromatic blue light peaking at 480 nanometers. And in this case, so that the same sort of type of protocol to record the phase response curve. And if we use the original photopic model, it qualitatively does produce, correct results, but quantitative agreement is not that good. While when we use our new melanopic model, then the agreement between the data and the model is actually, or rather between the model and the data is very good, and the error is reduced significantly, and it's actually even better than for the fluorescent light. So the second type of experiments that we need to test the model against is the dose response, meaning that the higher intensity of light generally results in the larger phase shift of the circadian oscillator. And again, here on the left, you can see results for the original, the photopic model, and experimental data for dose response to light for different light sources, fluorescent light, then monochromatic blue and monochromatic green. And what you can see in these results that even the experimental data sort of does not agree, or data sets do not agree with each other. There is a quite broad distribution, and the model also does not agree with either blue or green light sources or results for those light sources. If we recalculate all the results for melanopic irradiance and use our melanopic model for simulation, you can see the agreement is much better. The agreement also between the data itself is much better, but there is still quite a bit of a distribution there going on. And finally, the other effect of light on the circadian rhythms is the suppression of melatonin during nighttime. And what we have done, we have incorporated melatonin profiles in the model where the melatonin synthesis is triggered by the phase of the circadian oscillator, and then melatonin from the pineal is released into the plasma, and from plasma it diffuses to saliva, and it's also then broken down into metabolites and excreted by urine. So we have modeled sort of daily profiles of melatonin and 6-sulfatoxy melatonin, and then we incorporated the suppression of melatonin here directly from the light to this sort of the link between the circadian oscillator and the melatonin synthesis in the pineal. And the results are the following. So there were quite a few studies looking at the suppression of melatonin by light with different light sources. And here's an example. I think we have like 10 different light sources. 7 of them are monochromatic, blue, green, and red, and then others fluorescent and incandescent light. So here's 1.5 hours of light at night when you expect sort of strong suppression. And again, you can see when the data are plotted against photopic luminance and also the model simulations, none of that really sort of agrees with each other. But then when we replot the data against melanopic irradiance and use our new melanopic model, the agreement is really quite good. And similarly, we have results for the 6.5 hours of light and from similarly monochromatic and polychromatic light sources. And again, the melanopic model produces much better results, but here again, the agreement between the data is not as good, which we think probably related to the time-dependent effects of cones on the circadian phase, which we, or suppression, which we have not incorporated in the model yet. Okay, so just to finish off, I wanted to show you just a few slides on how we can integrate this circadian model with models for sleep-wake cycles and alertness prediction. So here's an example of shiftwork simulation in a full model of arousal dynamics, which incorporates the circadian oscillator, sleep, and alertness. On the left, you can see the raster with shifts shown in red and then sleep predictions in gray. And on the right, these are the time series of model variables. And for example, for the melatonin and for 6-sulfatoxy melatonin, we can see these are the predicted daily profiles. And then when we have a night shift here, both melatonin and 6-sulfatoxy melatonin are suppressed by light, but you still can see sort of what happens there with profiles and with acrophase measurements as well. And we have used this model for prediction of circadian phase in the real world shift work, where we had the data from nurses working shifts in ICU. And we used the model to predict circadian phase with the only inputs to the model being shift schedules from each nurse, their commute times, and the light. And what we found is that we can predict the phase really quite well for the group average. When looking at individuals, some individuals are predicted really well, while others, there's still room for improvement, but this is not particularly surprising because we used a group average model for predictions of individuals. So we really cannot expect like really good agreement here. Okay, so the take-home messages, just quickly to recap this, we've revised the dynamic circadian oscillator to incorporate the effects of light spectrum, so it can now be used with like any light source. And we have found that melanopsin sensitivity explained most of the experimental data, maybe with exception of the 6.5 hours melatonin suppression. And then the unified model that incorporates like all these different systems can be used to predict simultaneously circadian rhythm, sleep, and alertness, and we have incorporated it into a sort of web interface where you can test it yourself and run simulations if you are interested. And this is at the alertnessapi.com. And finally, I would like to just say thank you to the Sydney Chronophysics group. And you have seen a lot of these results were done by Taratech EA and Stuart Knock, and also thanks to my collaborators, and thank you very much for your attention.
Excellent. Thank you, Svetlana, for this really, really wonderful talk. I haven't seen any questions come in from the audience yet. I did have one question. Okay, Anne Skeldon raised her hand. Please unmute yourself. Why don't you ask the question and then, yeah, go ahead.
Yeah, very nice, Svetlana. Sorry if I missed it, but did you build the new light model into your alertness model?
Yes, so we have integrated the effects of light spectrum in the Kronauer model, and Kronauer model was already part of our alertness model. So yes, we've put everything together.
So then in terms of the calculating the melanopic lux that goes into your model, are you doing that from ActiWatch data, or how are you calculating the melanopic lux?
Yep, great question. So for these experiments, or the rather comparison to experiments, we just took the information about the light sources because that was provided in the paper, so spectral power density and irradiance. So that was fairly easy. In terms of ActiWatch, we did do some study, like trying to estimate melanopic irradiance from ActiWatch spectrum, which does have red, green, and blue filters. But that didn't really go very far because it's still tricky. I'm waiting for devices with melanopic irradiance in them.
Yeah. No, I was very interested because you know, there's some really nice things out there for calculating melanopic lux if you know the light source, but if you don't know the light source, it's a bit more tricky.
Exactly. Yeah.
Thank you.
We have one question from Luke Price. I just want to pick up on the second part of the question, which is about timing and temporal properties of the photoreceptors that provide the input to the Kronauer model. And so he says, looking further at timing, the feed-forward light drive from the Kronauer model has no persistency at lights off, whereas IPRGCs show some persistency. And have you thought about incorporating this time drop-off in the model?
Yeah. We did think about it. We haven't yet done any work on that, but yes, that's definitely a good point and something to look at, as well as the time-dependent effects of cones potentially on the circadian system.
Excellent. Thank you so much, Svetlana, for this great talk.